Hi guys, welcome back. Please subscribe to the channel. Today we'll be doing Physical Sciences Paper 1, Electrostatics. Let me take you through my presentation. Okay. Now, Electrostatics, Grade 12 Physical Sciences, brought to you by Google Foundation. So here, you've got a balloon, and then you've got a can. You can do this experiment at home. It's very easy. Just rub the balloon here with a tissue or cloth and see what happens to the can. Okay, focus of the lesson, the introduction. We'll also look at the law of conservation of charge. We'll look at the Coulomb's law. We'll look at the electric field around charged object, and then we'll also look at the electric field strength. Introduction. Electrostatics. This is a branch of physics that studies electric charges at rest or stationary. In other words, charges that are not moving. For example, have you ever felt a slight shock when you put a jersey over your head on a cold day? You know, those electric shock, when you're putting on a jersey. And then electric charge is the amount of energy or electrons that pass from one body to another by different modes like conduction, induction. There are two types of electric charges, for example, a positive charge and a negative charge. Bodies having no charges are neutrally charged. A charge is represented by the symbol Q, and then it's also measured in Coulomb, C, the SI unit. The coulombs is very big. For example, 6,25 ampere by 10 to the power 18 charges is equals to 1 coulomb. We must use small units by converting. For example, 1 MC is equals to 1 times 10 to the power negative 3 coulomb, and 1 microcoulomb. This microcoulomb is equals to 1 times 10 to the power negative 6 coulomb. And then 1 nanocoulomb is equals to 1 times 10 to the power negative 9 coulomb, and 1 picocoulomb is equal to 1 times 10 to the power negative 12 coulomb. Now, electric charges will exert forces on each other, and F is equal to K Q1 multiplied by Q2 over R squared. That's Coulomb's law. Like charges or charges of the same sign, they will repel each other, and then unlike charges will attract each other. If object loses electrons, it will become positively charged. If an object gains electron, it will become negatively charged. The charge on an electron is equal to, this is what we call elemental charge, 1,6 times 10 to the power negative 19 coulomb. The force is proportional to the product of the charges and inversely proportional to the square distance between them. That's, Coulomb's law. If we double, be careful here, if we double one charge, the force doubles. But if both charges are doubled, so it will be 2Q multiplied by 2Q, then the force increases by 4. If the distance between the charges, the distance is the R between the two charges, is increased, then the force will decrease, or vice versa. Now, let's look at the conservation of a charge. It said that the total amount of charge in a closed system remains constant. We also know that charge cannot be created or destroyed, but can only be transferred from one object to another. When charges are brought into contact, they must be added together and then divided by 2 to get an average charge. Okay, which is Q nu is equals to Q total, the sum of those two charges divided by 2. The change in charge, delta QA, for example, here you've got charge here, it will be equals to Q nu minus Q initial, which is charge A. And the change in charge QB is equal to Q nu from here minus QB initial. So this is the formula for calculating number of electrons that are transferred is equal to change in charge from here divided by elementary charge E. Let's look at example number 1. An object has an excess charge of -1,92 multiplied by 10 to the power -17 charge. How many excess electrons does it have? So here, how many excess electrons? So we have to calculate the number of electrons. So we can work with the formula N is equals to charge divided by elementary charge. So number of electrons equals to charge divided by elementary charge. So you are given the charge here, -1,92 multiplied by 10 to the power -17. Then you divide by your elementary charge, -1,6 times 10 to the power -19, which is equals to 120 electrons. So now let's look at example number 2. If two charged metal conducting spheres on an insulating strands which are identical except having different charge. Sphere A has a charge of -5 nanocoulomb and sphere B has a charge of -3 nanocoulomb. I then bring the spheres together so that they touch each other. Afterwards, I move the two spheres apart so that they are no longer touching. So suppose you've got two charges here, sphere A and sphere B, then we brought them together and then they will share the charges up until they get the average charge, the total charge, and then after that they separate. So the question here is saying that what happened to the charge on the two spheres and what is the final charge on each sphere. Here you calculate the Q nu, which is equal to Q1 plus Q2 divided by 2. So those two charges, when two conducting spheres are brought together to touch, it is as though they become one single big conductor, and then the total charge of the two spheres spread out across the whole surface of the touching spheres. When the spheres are moved apart again, each one is left with the half of the total or total original charge. So now here, you have to get the total charge between 5 and 3, -5 nanocoulomb plus -3 nanocoulomb, which is equal to -8 nanocoulomb. Here you get the total, and then now you divide the total by 2. So it will be -8 nanocoulomb divided by 2. So which is -4 nanocoulomb. So on each sphere. So now the each sphere, when they separate, it will be having -4 nanocoulomb each. Now let's look at the Coulomb's law. Coulomb's law is the electrostatic force of attraction or repulsion between two charged objects is directly proportional to the product of the charges and inversely proportional to the square of the distance between their centers. So now force is directly proportional to the product of the charges Q1 by Q2 is the product, and then this force is also inversely proportional to the square. This is square of the distance. So 1 over R2. So for us to change this proportionality, we must put a constant K. Here we put equal sign, and then also a constant K in Q1 and Q2 over R2. So now the F is the force, of course, in Newton, and Q1 and Q2, those are the charges in coulombs. And then R is the distance from the center of the charges. This is Q1 and Q2 from the center here, and then also at the center, you have got your distance R or D. You have got distance R there. And then your K also is your Coulomb's constant. Is given, this one 9 times 10 to the power negative 9 Newton meter squared per Coulomb squared. And then you also know that a force is a vector quantity, meaning that it has got both magnitude and a direction. So now let's look at the example 3. This example 3, it was taken from November exam 2017, grade 12. They're saying that two small spheres, X and Y, carrying charge of 6 times 10 to the power negative 6 Coulomb plus and 8 times 10 to the power negative 6 Coulomb, respectively, are placed 0.2 meter apart in air. So this is your X and this is your charge Y. So the thing that states Coulomb's law, the electrostatic force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So now the thing that calculate the magnitude of the electrostatic force experienced by charged sphere X. So here you work with F is equal to K Q1 by Q2 over R squared. Here you're given R. So you have got charges X and Y. You put here and also you put a constant, Coulomb's constant. So the force of traction or repulsion between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That's Coulomb's law. Number 2, F is equal to K into Q1, Q2 over R squared. So you put your constant K, 9 times 10 to the power 9, then your Q1 it was 6, multiplied by 10 to the power negative 6, then your Q2 is 8 multiplied by 10 to the power negative 6 over 0.2. Don't forget to square here. Don't forget to put squared here for you to get 10.8 Newton. So that's the magnitude of the force. Now, example number 4. This was taken November exam 2018, grade 12. So they're saying that a particle P with a charge of 5 times 10 to the power negative 6 is located 1 meter along a straight line from particle V. This is particle P, and then this is particle V. And its charge is 7 times 10 to the power negative 6. Okay, now a third charged particle Q. So here you've got the particle Q at a point which is X meters away from P. So from P to Q, we've got distance of X. Experience a net electrostatic force of 0 Newton, 0 N. So which means from here, if from P to V, the distance is 1, and then from P to Q, the distance is X. It means that the distance from Q to V is 1 minus X. Just subtract, X from this distance, 1 meter. So now, how do electrostatic forces experienced by Q due to charges on P and V respectively compare with each other? So in other words, the charge from here to P, it will be moving to the left, and then the force experienced by Q to V, it will be to the right. All right. So now for you to answer this question, you say the force experienced by Q due to P is equal in magnitude, right? But it will be in opposite direction by a force experienced by Q due to V. Now, state the Coulomb's law. We've done this. The electrostatic forces between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So now calculate the distance x. So we want to calculate this distance x. So for you to get the distance x, you can calculate the force, the force PQ, F of PQ, and then you can, of course, you have the distance of x, and then you can also calculate the force of PQ, and then you can also calculate the force between VQ, which is the distance here is 1 minus x. And then we also told that the net force is 0. So F net is equals to F1 plus F2 is equals to 0. So F1 is equals to negative F2. So now you will have the force experienced by Q due to P must be equal in magnitude but opposite in direction to the force experienced by Q due to V. I've said this. And now the force of attraction or repulsion between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That's the Coulomb's law. So now on number 3, we are saying that force is equal to K of Q1 and Q2 over R squared. Now you put your 9 times 10 to the power 9. And Q, here you've got 5 times 10 to the power negative 6. The force from P, so that you are PQ, F of PQ, right? And then the R, the distance there is X squared. So now you multiply this and this, you get 4,5 multiplied by 10 to the power 4, Q, right? Over X squared. Then now you go again, you calculate the force between VQ, which is equals to 9 times 10 to the power negative 9, multiplied by Q, multiplied by force of V, which is 7 times 10 to the power negative 6, all over by 1 minus X squared, right? Don't forget the squared here. So it will give you 6,3 multiplied by 10 to the power 4Q, all over by 1 minus X squared. So we're told that the F net is equal to 0 Newton. So now F of PQ minus F of VQ, because the other one is going this side and then the other one is going this side. So they are in opposite direction. So when you transfer this to the other side, it will be F of PQ is equals to F of VQ. So in other words, you equate the two forces. You equate the two forces. So you'll have 4,5 from here, 4,5 multiplied by 10 to the power 4Q over X squared, which is equal to 6,3 multiplied by 10 to the power 4Q over 1 minus X squared. So when you are here, you start by dividing both sides by Q, and then this Q and this Q will cancel out. And then now you are left with this unit here. So now you then cross multiply. So this and this will multiply each other, and this will multiply each other. So after multiplying each other, you then introduce square root both sides. Square root on the left and then square root on the right, for you to get 2,12 multiplied by 10 to the power 2 into 1 minus x, which is equals to 2,51 multiplied by 10 to the power 2 x. Then you then solve for x, and then your x should be 0.46 meter away from P. That's the distance, the distance x. And then your home task, you are given 3 spheres, identical metal sphere Q1 and Q2 and Q3 are placed in a vacuum. Each sphere carries a charge of -4 microcoulomb. The sphere are arranged in such a way that Q2 and Q3 are 3 millimeter each from Q1, as shown in the diagram. Okay, now see the Coulomb's law. Draw the first diagram showing the electrostatic forces exerted on Q1 and Q2 and Q3. Calculate the net force exerted on Q1 by Q2 and Q3. This is your home task. Work on this. You can submit. You can, if you've got any question, you can submit on the comment. So let's look at the electric field. So an electric field is a region or a space in which an electric charge experiences an electric force. So electric field are represented by the field lines. Electric field is also a vector quantity, meaning that it's got magnitude and a direction. So properties of electric field lines. These field lines, they will never intersect each other. In other words, they'll never cross each other. So they are directed from positive to negative. So they move from positive to negative. They are also perpendicular to the surface charge. The field line is strong when the lines are close together, and it is weak when the field lines are moving apart from each other. So now, electric fields, representing electric fields, suppose you've got a negative and a positive charge. So now, this is a positive charge. Now the electric field will be pointing, the arrows will be pointing outwards. In other words, it's diverging. And then for a negative charge, the arrows will be pointing inwards. In other words, they are converging. So the opposite charges here. Suppose your charges from here, from the positive, we said they move from positive to negative. So the arrows will be moving from positive to the negative charge, right? And then for the like charges, there's some repulsion here. This is attraction, and here we've got repulsion. So the arrows will be pointing outwards and outwards. It will be diverging. And then now, oppositely charged plate. Now these field lines here, they are uniform, right? In other words, they are equally distributed, and then they're moving from positive to negative. So let's look at the electric field strength. Electric field strength at a point is the electric force per unit positive charge experienced at the point. So electric field strength is also a vector quantity. So it's given by the following formula. So E is equals to F over Q. Right? We also know that the Coulomb's law is given by F is equals to Q1, Q2 over R squared. So if you come and substitute this F here, and then this, which means that the Q and Q1 here, it it will cancel out. Then you are left with one Q here. So your E, it will be E is equals to K Q over R squared. Now, your E is the electric field strength in Newton per Coulomb, and then F is the force in Newton, obvious. And then Q from here is the test charge. And then electric field strength is also in Newton per Coulomb, charge is in Coulomb, and R is the distance in meter. Make sure it's always in meter. And then K is a Coulomb's constant, 9 times 10 to the power 9. So now, let's look at the example. This example was also taken from November exam 2018 to 12. So now, a small metal sphere Y carries a charge. Here you've got a charge of 6 times 10 negative 6 Coulomb. This is metal sphere Y. Draw electric field pattern associated with the sphere Y. So now you can draw those patterns. I said for a positive charge, it will be, the arrows will be pointing outwards. So in other words, it will be diverging. So that's saying that if 8 times 10 to the power 13 electrons are now transferred to sphere Y, so this sphere Y, calculate the electric field at a point 0.5 meter from the sphere. So now you are given the electrons here which are transferred. So from the electrons, you have to get the charges, number of charges which are transferred. So you have to multiply these electrons by the elementary charge, 1,6 times 10 to the power negative 19, for you to get the charge, the real charge, So now after getting the charge here, you then add that charge with the sphere Y. You add the charge with this one of Y, and then when you are done, you then use the formula of electric field is equals to KQ over R squared. You are given the distance here, and then now it should be simple. So now this is the positive charge. The arrows are pointing outwards, and then now for number, you say your Q is equal to number of electrons multiplied by E, right? So number of electrons which are transferred, it's 8 times 10 to the power 13, and then multiplied by elementary charge, negative 1,6 multiplied by 10 to the power negative 19. And then now you get negative 12,8 times 10 to the power negative 6 Coulomb. So now the net charge on the sphere, the two sphere, you've got sphere Y here, 6 times 10 to the power negative 6, and then you add it with this charge, negative 12,8 multiplied by 10 to the power negative 6. So you get the Q total or Q net, which is equals to negative 6 times negative 6,8 times 10 to the power negative 6 Coulomb. Right, then you write the formula for electric field E is equal to KQ over R squared. Then you put your constant there, 9 times 10 to the power 9 multiplied by the Q net, 6,8 multiplied by 10 to the power negative 6. So here you don't put negative, so over 0.5 squared. So, and then it will give you 2,45 multiplied by 10 to the power 5 Newton per Coulomb, towards the sphere Y. And then it should be simple. Your home task. So an isolated point charge Q here, located in the space as shown in the diagram below. Point charge Q contributes to an electric field as shown. Point X is located 3 millimeters away from charge Q. So define the electric field at a point, calculate the magnitude of the electric field at a point X. Point point charge R carrying a charge of this 6.5 times 10 to the power negative 12 coulomb is placed 3 millimeter away from X, as shown in the diagram. Here. So this is your X and then this is your R here. So the thing that calculate the net electric field at point X. Don't forget to convert here the millimeters, and then this should be simple. And then we also given the direction here. So if you've got any question, you can submit on the comment. You can ask in the comment, I'll respond. Thank you very much. Don't forget to subscribe. And don't forget to like, share, and subscribe.